Hello everyone. So today I'll be talking about walking in the shadow, a new perspective on descent directions for constrained minimization. This is joint work with Swati Gupta and Sebastian Pukuta. This is the outline for my talk today. I'll first introduce the problem, then I'm going to present our parametric projections framework. Then I'm going to talk about two different algorithms that we propose, give some computational experiments, and then finally conclude. So in this talk, we consider the problem of minimizing a mu strongly convex and L-smooth function over a polytope P. And we assume access to our function via first order oracle, which just means that given any point x in the polytope, this oracle will give us the function value and the gradient at that point. So this setup is important because this problem appears in many machine learning and combinatorial optimization problems, such as structured supervised learning. We have other examples on the slides here, but in all of those examples, we're minimizing a smooth and convex function over a polytope. So this is the main problem of interest, and there exist two main paradigms to solve this problem. The first is a class of methods known as conditional gradient methods, and there we assume access to our polytope via linear optimization oracle. And these methods have made a really big comeback in the past decade or so due to their applicability in large-scale optimization and machine learning problems, and we see that here from these very recent references. On the other hand, there are these mirror descent type algorithms and their variants, and those assume access to the polytope via projection oracle, which is a lot more expensive than linear optimization. So let's quickly review these methods. So this is the basic conditional gradients algorithm. And in each iteration, the algorithm computes the feasible direction that's most aligned with the negative of the gradient. And it does so by solving this linear optimization problem in step 3 of the algorithm. And upon doing so, in the example we have on the slide, it takes us to this vertex. And this vertex VT is known as the Frank-Wolf vertex. I'll use that terminology in the talk. And this gray descent direction is known as the Frank-Wolf direction. And then the algorithm will basically do a line search along that descent direction to minimize the function value to obtain the next iterate xt plus 1 as follows. So this algorithm is very simple and efficient because all the iterates are feasible, and so it does not require projections. However, it trades that efficiency and feasibility of iterates with the quality of the descent direction chosen. And we see that here because this gray Frank-Wolf descent direction is not really well aligned with the gradient. And so this algorithm only has sublinear convergence, but it turns out that it can achieve linear convergence by augmenting this basic algorithm with these so-called away steps. And what are these away steps? These away steps were basically in each iteration, we additionally compute an away vertex to move away from. And this is done by solving this linear optimization problem in the box that we see in the bottom left here in the slide. And back to our example, upon doing so, this vertex is AT, and our away descent direction is this green dashed line. And then again, we do a line search along that descent direction, update our iterate as follows. There are many ways to choose that away vertex proposed in the literature, and I'll talk about that more later on in the talk. On the other hand, we have these projected gradient methods, and here we have the basic PGD algorithm, where in each iteration we take a 1 over L step size in the negative gradient, and then just project that back as we see in the example here in the slide. And the convergence rate of that PGD algorithm is optimal in the sense that it only depends on the condition number of the function L over mu, and it does not depend on the dimension nor the geometry of the problem. This is a big advantage of PGD methods that CG variants do not have. However, projections are expensive, and in this paradigm, they're treated as a black box oracle without really exploiting the structure of the problem. And this is something that we will address in this talk. We see here that this PGD algorithm does really well and has optimal convergence rates. So in this talk, we asked the question, can we use that framework to deduce what the best feasible descent directions are and improve upon the convergence rates of CG variants? And to do that, we're going to need the parametric projections curve. But first, we're going to define the shadow of the gradient, hence the name of this talk. So in this talk, we're going to let pi p be the Euclidean projection operator onto our polytope P. And for any point x in the polytope, we define the shadow of the gradient as this limit quantity we see here in the slide. And this is just basically the directional derivative of the projection operator. So this quantity has been looked at before in the literature. In particular, in 1974, Tapia and al. Were the first to show that this directional derivative is the projection of the gradient onto the tangent cone at x, or the cone of feasible directions at x. However, we give it the name shadow because it's literally the shadow of the gradient onto the polytope. So if you look at that example here, we start at xt. We have the negative gradient here at xt, and the shadow is just this orange arrow we see here. So why do we care about the shadow? We care about the shadow because of this lemma here, which just says that the shadow is the feasible direction in the polytope that's most aligned with the gradient. In unconstrained optimization, we know that the negative gradient is the direction of steepest descent, However, it may no longer be feasible in constrained optimization, and so the shadow of the gradient is the analog of that in constrained optimization, and it's locally the optimal descent direction that you want to follow. So now we're going to talk about the structure of the projections curve, and this is the main result in this talk, and it's central to our analysis and our algorithms. So for any point x0 in the polytope, we let g of lambda be this projections curve at x0 parameterized by the step size lambda. And we have this theorem here that completely characterizes this curve as a piecewise linear curve, where the breakpoints of that curve occur at points where there's a change in the normal cone. So let's explain that with an example. So consider this polytope P. We start at x0 and we consider the negative gradient at x0. And we vary the step size along that direction. Now we see in this figure here that the projections curve is actually this orange curve in the figure. And we see here that it is indeed piecewise linear. So the first breakpoint is x1, and we see that between x0 and x1, we have the first linear segment, and the normal cone is constant there. We only have one active constraint that's active throughout. But then at x1, at the breakpoint, we add a new constraint. Moreover, x1 corresponds to a projection with a step size lambda1 minus. And the interesting thing is that in the interval between lambda1 minus and lambda1 plus, we remark that the projections curve will keep projecting back to x1. So this curve does not change with the same speed as the step size. And then this process of creating these linear segments where the normal cone is constant and adding new constraints at subsequent breakpoints will continue until we reach the endpoint of that curve. A very nice property that we show is that you can constructively trace this entire curve using iterative line search and shadow computations. In particular, consider the I-1th breakpoint, xi-1. To compute the next breakpoint xi, all you need to do is consider the negative gradient at x0. So this is the original gradient direction that we're interested in. We're not changing the gradient here. And then we compute the shadow at xi-1 with respect to that original direction and do line search along that direction to obtain the next breakpoint xi. So now we're going to use this projections framework and shadow computations to unify a lot of existing results in the literature. So we gave a constructive procedure in the previous slide to trace that entire curve. And so we see here that actually we can use that same procedure to recover the PGD step, because the PGD step just, it lies on the curve and corresponds to when lambda is equal to 1 over L. But now the interesting thing is that we also show that you can use the same procedure to recover the Frank-Wolf vertex. In particular, we have this theorem here that says that if the Frank-Wolf vertex is unique, then the endpoint of that curve is indeed the Frank-Wolf vertex. We call that the Frank-Wolf vertex was the vertex that we were computing in the CG algorithm. So if we look at that example here, we start at xt, we have the negative gradient at that point. The projections curve is the yellow curve, and vt is the endpoint of that curve, which is the Frank-Wolf vertex. This gives a novel connection between PGD and CG variance, and it also gives a new view of these Frank-Wolf steps. Now, the nice thing is that also the shadow gives a true estimate of primal gaps, meaning that at a point x, the norm of the shadow is 0 if and only if x is optimal. And note that the gradient does not satisfy this property, because if the optimum is constrained, then the gradient is not 0 at that point. Also, a nice thing is that we can use the norm of the shadow as a proxy, as a tight proxy for the primal gap for strongly convex functions, as we see in the inequality here given in the slide. Finally, we also note that we can use our framework to obtain the best away point and hence obtain the best away direction. However, I'm not going to get into the details of that talk, and I'm not getting into the details of that here in this talk, but bear that in mind for later on. So now, inspired by these shadow steps and the structure of the parametric projections curve, we propose a shadow walk algorithm, where in each iteration we walk along the shadow at an iterate using line search until we have sufficient progress. This is done by this trace procedure here, where at an iteration t, we fix the gradient at that iterate nabla f of xt, and we trace the projections curve starting at xt with respect to that gradient direction. And we do this using our constructive process that I previously described, which is composed of iterative line search and shadow computations. And this trace procedure will trace that projections curve using that approach and find the minimizer of the function f over that curve instead of the whole polytope. So a nice property of the shadow walk algorithm and the trace procedure is that it only requires one gradient oracle call per iteration. Remember that to trace the projections curve, we do not change the gradient, we fix the gradient. So we can now show the following convergence result, which shows that the primal gap of the shadow walk algorithm decreases geometrically as follows. But this assumes that that trace is a single step. And so we have the same linear convergence rate as PGD. However, we know that in trace, we actually do multiple line search and shadow computations. And so the number of oracle calls made to shadow and line search oracles to obtain an epsilon accurate solution is O beta L over mu log 1 over epsilon. So we incur this additional factor beta, and beta is the number of breakpoints that the trace procedure must visit. So we just described the shadow walk algorithm, where we enter this trace procedure every iteration, but this can be very expensive. So to improve the efficiency of the algorithm, we propose adding these Frankov steps to the algorithm. Remember that the Frankov steps form the endpoint of the projections curve. And so they greedily skip a lot of facets by wrapping maximally over the polytope. And hence the idea is that by introducing these steps, we can potentially avoid entering trace. So this is the shadow CG algorithm. Let's understand what it does with this same example that we've been using. So at XT, we can either take the Frankov direction, which is the green direction we see here in this figure, or we can trace the projections curve, which is the yellow curve that we see here in the figure. So we choose what to do, or which descent step to take based on this test in line 4, which is actually a dual gap test. But this is sufficient for linear convergence. And we have the same exact theorem as before, but we additionally incur this d squared factor in the convergence rate, where d is the diameter of the polytope. And so we see that the convergence rate is theoretically worse for shadow CG, but the algorithm is more efficient because of the addition of Frankov step. And we'll verify that computationally later on. So now I just want to take a step back and compare our results with some existing results in the literature. This is a table that summarizes some CG variants, their technique, meaning which, how they choose their wave vertex, what descent directions they choose, etc., and their convergence rate. So first we see that all those convergence rates depend on kappa, which is the condition number of the function. However, all the CG variants, the rates also depend on some geometric constants. I'll talk more about the geometric constants in the next slide. However, for now, just note that we do not have that dependence in our algorithms. So now I'm going to focus on two results. So the first is by Garber and Hassan 2013. So what they do is they, instead of computing the regular Frankov vertex, they constrain the Frankov vertex to be within a ball around the current iterate. And so by doing that, they're emulating a shadow computation. So their algorithm can be understood as an approximation of shadow walk. More recently, Bashiri and Jan, they compute their away, they find the best away vertex that gives the best alignment with the negative of the gradient. However, I said before that we can use our framework to obtain the best away point and hence find the best away direction. And so their algorithm can be understood as an approximation of shadow CG because they also mix Frankov steps and away steps like we do in our algorithm. And when I say approximation, I mean that these algorithms pay for these approximate computations of shadow using these geometric constants. So for example, the away Frankov variant of Lacoste, Julia, and Yagi in 2015, they show that the number of steps to get an epsilon error is O kappa d over delta squared log 1 over epsilon, where delta is the pyramidal width, it's a geometric constant, and d is the diameter of the domain. In the triangular polytope example here we see on the slide, actually the pyramidal width delta is sine of theta over 2. So we see here that as we change the angle theta, the pyramidal width will dramatically change. However, our convergence rate rather depend on this beta factor, which is invariant to such geometry deformations, preserving the facial structure of the polytope. In that sense, our rates smoothly interpolate between the rates of CG variance and PGD. So finally, to present some computations, we consider the video colocalization problem from computer vision. And this amounts to minimizing a quadratic function over the flow polytope. And in this plot here, we benchmark various CG variants, PGD in our algorithms. On the y-axis, we have primal gap. And on the x-axis, we have iteration and walk log time. On the plot on the left, we see that shadow CG and PGD are superior in iteration count compared to CG variants. And on the plot on the far right, we see here that if we assume a shadow oracle, meaning that we don't factor the time it takes to compute the shadow into account, we see that shadow CG outperforms all the other variants. We report the same behavior for the duality gap, but finally, we compare the cumulative number of shadow steps taken by shadow walk versus shadow CG in the plot on the bottom left. And we see here that shadow walk takes significantly more shadow steps, and this is due to the introduction of Frankov steps. Similarly, in the plot in the bottom right, we see that every iteration shadow walk makes a lot more calls to a shadow oracle compared to shadow CG. Again, this is due to the addition of Frankov steps. So finally, to conclude, we consider the shadow of the gradient as a descent direction. We presented this novel framework for unifying and analyzing various first-order methods, and inspired by that framework, we proposed two different algorithms and verified their performance computation. These are the references for my talk today. Thank you so much.